Okay, good good day, class. Welcome back to our subject here in ESci132, your mechanics of deformable bodies. And as you can remember on our previous topic, we are already on our 5th module, which was about bending. And we have created a very important equation that will relate your normal stress and your bending moment. And we learned that that formula was the flexure formula. But however, that formula is very limited only to materials that are homogeneous. Again, when you say homogeneous, the whole material is made up of only one material. But how about we have composite beams? And that is what we are going to talk this morning. We are going to talk about the flexure formula that is applied on composite beams. So for the goal of this lesson is that we should be able to solve the maximum bending stress of a composite beam and be able to graph the profile view of the stress distribution of a composite beam. A composite beam, siguro kuha pa mo ka sabot si composite beam, is basically a beam that is again made of two materials. So for example, I have a beam here. Ito sa tanaw ng side view ha. So we have this beam. This beam is a composite beam in which the upper half of this beam is made of a material that is stiff, and sa lower half of this beam is made of a material that is less stiff. Dili siya kayo stiff compared sa babaw. Okay? Let's call this one your material 1 and your material 2. And again, there is a moment applied to this. We all knew nga kung magbutang tag moment ani nga beam, there will be bending nga mahitabo. And then, di ba, kung naibending, nai-portion ani nga beam nga mo-compress, na po portion ani nga beam nga mi-inat. And we will know kung asa na dapit, nag-inat asa na dapit ang nag-compress, kung nakahibaw ta kung asa ang neutral axis. But let's just say that in this case, your neutral axis is located right here. And therefore, the normal strain will behave like this. Okay? So, maninitabo sa atong strain. Pero, the question is, how about the stress distribution of this one? Will this still behave in this kind of distribution? I don't think so. Why? Because na yung mga materials, ang stiff material, di ba, kung nasa certain elongation, taas ang ilang stress nga mahitabo ana. Di ba, naka-remember mo sa atong stress strain diagram? Kung stiff material, makaingon ta nga, dako ang iyang modulus of elasticity. Kung dili stiff nga material, mas gamay siyang modulus of elasticity. Since kanisiya, ing-ani daw kung tayang iyang behavior sa iyang strain, take note, the word strain, morning behavior sa iyang strain, linear silang relationship, ang 1 ug 2, linear ang pag-compress o pag-inat sa iyong material. But, diha sa itong stress, lahi na silang behavior. Ang kaning mas stiffer nga material, mas dako siya og stress compared sa kadong material nga gamay lang og modulus of elasticity. Okay? So therefore, perhaps this one will show a stress distribution of this. Diba? Okay, again, mo na ito neutral axis. Huwag po na. Okay? So this is how your stress behaves in a composite nga beam. Dili siya parehaan ni, kay ang atong strain, again, linear lang iyang relationship. Kay naka-glue man na sila together at this point. So, parehas ra na sila og pag-inat. Pero diri sa atong stress, lahi na silang stress nga gidala. So, how are you going to graph profile view. So basically this one is your profile view. Yung kita na ang side view sa behavior sa stress. So how can you graph a profile view of a composite material? Ato tanaan ang side view na pud ani. Ang atong goal, we have to apply the flexure formula sa ani nga beam. But again, we cannot apply the flexure formula because this beam is not homogeneous. So, question, is there any way to make this composite beam a homogeneous nga beam? There is actually a way para ma-homogeneous na siya. And that is what we call the transformation. So you have to transform one of these two materials into the other material so that that material will be homogeneous. Okay? How can you transform that material? In this case, so if your beam 1 is stiffer than your beam 2, then the modulus of elasticity of your beam 1 is greater than the modulus of elasticity of your beam 2. Okay? So, sige, let's say, ing ani. Ato da kuntahay. Ang goal na to, ganahan na to i-transform ni ang kaning atong 2 into 1. Okay? So, ang 2 ganahan ni mo himuog 1. So, unsa may mahitabo? Less stiff ni nga material compared sa atong 1. Para maka-same sila og stress, ang imong buhaton, siguro, ato, panipson ang 2. Diba? Kay, kung less stiff ni siya, ato pagamyo ng area para pareha siya og stress aning atong upper nga beam. But, if ang atong 1, ganahan na ito himong 2, what will happen? Then, same dimensions ang imong 2, pero ang imong 1, ang mas nidako. Okay, so this is your 1 and this is your 2. Okay? So, kung imo gi-transform ang this one into this one, then this will be homogeneous. Or kung imo i-transform ang kaning isa into this one, this will be homogeneous. And how can we transform that one? Then we have this relationship. Your n is equal to E1 over E2. And this is what you call your transformation. Okay? So that is your transformation factor. In which, in this case, we have to change the width of the beam we want to transform, or this one. Question, ngano ang width man ang atong i-change? Dili man ang height. Kaya kung ang height ang atong i-change, malahi na ang iyang profile view sa iyang strain distribution. Maabot na dira. So, dili na mao. Diba? Kay kutob ra man ang atong strain diri nga portion. So, therefore, para consistent sa atong strain, instead of ang height ang atong i-change, ang width ang atong i-change. Okay? And again, that will be accomplished by using your transformation factor. So how can you use your transformation factor in transforming this one into this one? Diba? Ang atong transformation factor. So this one is higher compared sa ani niya. So therefore, this one will probably be greater than 1. So your n here will probably be greater than 1. So, unsa na may mahitabuan na? Ang imo lang buhaton, i-multiply nimo ang length ani niya, ang width ani niya, by the n to get this bigger width. Okay? And this is again if ang imong E is higher sa imong i-transform. Pero in this case, ang imong ganahan i-transform kay ang 2, ganahan nimo himong 1. And now that will be E2 over E1. And we know that this one should be less than 1. Kaya diba, ang E1 man ang dako kaysa imong E2. So kung imo i-divide ang mas gamay sa imong mas dako, that will be less than 1. So in this case, kung W ang imong initial nga width and imo gimultiplyan anang N, then mas mogamay ang iyang width. Okay? Mo gyapon N times W. And once gani nahibaw-an nimo ang bago nga mga widths atong ipang transform, then you can now apply the flexure formula since the material now is already homogeneous. Okay? So let's have this example. So we have this beam, this composite beam. The red part of the beam is made of wood and the blue part is made of steel. Okay? And we have to determine the normal stresses at point B and point C. And aton lang po di-add, we have to make a profile view of this one. Okay. So, what are we going to do? Since this one is not yet homogeneous, so we have to make this one homogeneous to apply the flexure formula later on. And how are we going to make this one homogeneous? If given daw ang atong modulus of elasticity sa atong wood to be 12 gigapascals and the modulus of elasticity sa atong steel to be 200 gigapascals, then how are we going to make this one homogeneous? Kay di ba? Ato tanan ng cross section ani pa front view. Gana. And gananta, siguro, ato i-transform ang wood into steel. Sige, mao na tong goal ha. We are going to transform your wood into steel. So therefore, we have to change this width of our wood. And how can we change the width of our wood? And let's call down, what will you expect kung ato i-convert kani into steel? Mubaga ba siya or munipis? Para pareha siya og strength. Dapat mo nipis. So, atong goal mahing ana na siya. Di ba? So therefore, unsay mahitabo? Let's call this one as W prime. Mao kun tayo na atong bag-o nga width. So to get our new width, all we have to do is to multiply the initial width, which is kani, by N. Unsa man ning atong N? Para mo gamay ning atong width, unsay dapat value sa atong N? Should it be greater than 1 or should it be lesser than 1? It should be lesser than 1. So, unsa man na, para mo lesser than 1 siya, di ba kay ang N is equal to E over E. Pero, para lesser than 1 siya, asa may ato ibutang sa numerator, asa ato ibutang sa denominator. Of course, ang numerator ang wood. Ang denominator ang steel. Para 12 divided by 200. Okay? So, therefore, initial width niya is 150 millimeters multiplied by 12 over 200. And your new width na is 9 millimeters. Okay? So, na-transform na nato ang wood into metal. Okay? But, how about sige, nga niya ito ganahan. Ganahan ta nga, i-convert na to ang metal into wood. So, kung metal into wood ka, you will expect that the width of the metal will be greater, will be bigger para magka-equal siya sa strength sa atong wood. Okay? So therefore, ang imong N ana mahitabo na is 200 divided by 12. So kung ang imong metal ang imong ganahan i-convert into wood, ang imong buhaton is W prime is equal to 150 times 200 divided by 12. And that will be 2,500 millimeters. And 2,500 millimeters is not a good nga kuan. Imong ihatag 2.5 meters ang imong width. Pero nara na nimo kung asa imong preference. Pero I'd rather choose the 9 millimeters kay gamay ra siya. So mo na atong gamiton. And therefore, this one, instead of having this one, na-transform na siya into this one. Okay? And this one, again, is 9 millimeters. 150, sakto, 20, and 150. And now, we can apply flexure formula. So, di ba? We all knew that your maximum bending stress is equal to MC over I. We already know the moment. We don't know the C and we don't know the I. So we have to look for the C and the I. Diri. And how are we going to solve for the C? Diba? Atong gamiton ang Y bar. Is equal to summation of area times Y. Okay. And makuntahin atong dito nga line. So, therefore, mo na itong first and mo itong second. So, let's do this. Area sa aning babaw, 150 times 9 millimeters. Y bar, 150 divided by 2 is 75. So, 20 plus 75, that is 95. Plus, kaning gamay, 20 times 150 multiplied by centroid pa dong sa ubos, that is 10. Ang kaning 95 ha, gikan diri pa dong sa centroid ani. So 20 plus 75, 195. Over 150 times 9 plus 20 times 150. And your Y bar is equal to 0.03638 meters. Gi-convert na siya dayon into meters dere. Okay? Or that is equal to 36.38 millimeters. So now, let's determine the moment of inertia of this one. The moment of inertia from the neutral axis, let's say na diri ang neutral axis, which is 36.38 millimeters. Saman. Una gyapon ta aning first. So that is B, 9 times height of 150 cube over 12. Yeah, parallel axis theorem, 9 times 150 times distance sa centroid ani padong sa neutral axis. That is 95 minus 36.38 squared. So, muna itong 1 plus kaduhan na pod base ani which is 150 times height of 20 divided by 12 cube plus 150 times 20 times distance na pod sa centroid diri padong diri 36.38 minus 10 squared. And you will have an I of 9.358 times 10 to the negative 6 meters to the fourth. Okay? So we now have solved MCI. So we can solve for your stress max. So ato sa to tan-an ang profile view sa katong homogeneous Ya, di ba? Morning neutral axis. So what is the maximum bending stress? Sigma max is equal to M. Pila imong moment? 2 kilonewton meter. Pila imong C? Ay, di ba, ang distance ani kay 36.38. And kibaw man ta nga ang distance ani is 170. So, perhaps, mas dako ang distance ani. So, that is 170 minus 36.38. Sakto? Over, so morning C, morning M, ang I, 9.358 times 10 to the negative 6 meters to the 4. I-convert pa ni siya into meters. Okay? So therefore, this is 0.170 minus 0.03638. Okay? And therefore, your sigma max is equal to 28.6 megapascals. Okay? So, diri di ay (28.6 megapascals. Dira sa babaw. Okay, ba mo man C, mo may pinakalayo. How about diri? Kani. So, atong gyapon to gamiton. 2 times sa may butang diri. Kanina lang 36.38 kay di ba ang distance ani is 36.38. So, you will get ang imong shear diri sa, let's say this is C, is equal to 7.78 megapascals. You're still using this equation but instead of using your C, what kay imong gi Y, my over I. Kay ang Y mo aning 36.38. Okay? Are we done? We're not yet done. Why? Because we have to transform this back into its original nga shape. Ato ibalik ang kaning steel sa ibabaw into wood. How are we going to transform that one? What will you expect? Will the stress sa atong diri nga portion maximum will be higher kung ato ni transform into wood, or would it be lower? Given nga lower og modulus of elasticity ang atong wood. So with great strains, gamay lang iyang stress. Atong steel, na great strain, so dako ang iyang stress pod. So therefore, this one, kung ato ni i-transform into wood, mo gamay ang stress. Okay? And we are still gonna use that transformation factor to get your stress. So, the original stress is equal to, sa naman po ni, so since nag-expect nga mo gamay, so dapat less than 1 ang atong transformation factor. So, that is 12 divided by 200 multiplied by 28.6. Okay? And therefore, that one will be equal to 1.71 megapascals. So, pasabot ana, balik na punta sa profile view. So, na-transform na nila ako balik ha into this cross-section. Ning ana na siya. This one is steel. So, ang nahitabo ana, so, ang stress diri sa maximum is 1.71 na lang. Okay? Ni gamay may yung stress sa original. So, naingana. And then, diri, same gihapon. But, pag-abot niya diri sa atong kaning ilawom, ilako na po na siya. Since this one has not transformed, okay, therefore, parehas sa siyag value sa dira sa ubos. Pero, how about ang values diri? Kani ug kani nga values. You can determine the values of this one by using my over I. So, ang imong pangitaon ani, mo i-change diri ang distance from your neutral axis dira. To get the value of this one, imong buhaton is to use your my over I, in which ang imong y is the distance from here to here. Kana. Okay? And once you get that one, then, to get this one upod, mao na po ni, 12 over 200 times ang value sa ani. Okay? To get this normal stress. Okay? So, mao ni ang profile view sa atong composite nga beam. And we found out that the stress at B is 1.71 and the stress at C is 7.78. Understood? Sige. So, karon, ngano nag-topic ta og ing ani? Naaday mga beams ngayong ani. Nabatay nakitaan nga beam nga ang babaw kay wood, ang ubos kay metal? Siguro wala. Pero unsa may beam nga atong nahibaw-an nga composite siya. That is our reinforced concrete. Because that's why I'm dealing with this one. Kaya nagduha-duha ko kung importante ba ni siya. Pero ako lang gi-discuss because naatay reinforced concrete. And that reinforced concrete is a composite nga beam. Ano man? Because, diba, maoning cross-section sa atong concrete kuntahay. Kaya kung atong concrete, gigamit siya for beam, then, kailangan na i-reinforce. Because your concrete cannot support tension. And that will be our topic on the next lesson. See you on our next lesson.